Greetings. My name is Mike Levis, and I'm an instructor with the Mountain Hood Ski Patrol Avalanche Program. The topic of this presentation is snow stability assessment. And what we're really trying to do is answer the question, what data will we look at in order to make safe decisions about travel in avalanche terrain? So during this module, we're going to give you the tools to answer that question, hopefully. As part of travel planning, we will look at many sources of information: weather data, snowpack data, and terrain information. We will look at data well before we travel, on our way to the trailhead, and during our travels. We will continuously integrate new data as it becomes available. All this data gathering is to paint a picture of stability and risk as we travel. What is the likelihood of a slide, and what will be the consequences if a slide does occur? However, not all information is equal. In the following discussion, we will talk about how to prioritize the information we're receiving. Throughout all this, please keep in mind the words at the bottom of this slide in red. Evidence of instability outweighs evidence of stability. Let me repeat that. Evidence of instability outweighs evidence of stability. All of the tests and data we look at are really to identify instability, not prove stability. Our goal in this module is to practice looking at the avalanche triangle data, weather, terrain, and snowpack, to identify factors that may contribute to instability. As I mentioned before, we will always outweigh evidence of instability more heavily than evidence of stability. We'll then take all this data and hopefully make sound decisions about travel and avalanche terrain. A useful tool we use is called the bullseye approach. In the bullseye approach, we start broadly looking at historical data for the most part, and then gradually refine our view of data to much more localized in real time. In the outermost ring, we'll look at weather history, topo maps of the area to be traveled, recent avalanche events, and forecast data for the area and time of interest. We'll make a guess at what we think the snow structure will look like on the mountain when we dig a pit. This is analysis we do at home as part of our overall trip planning. In the inner ring, we have data that is more immediate and localized to our area of travel. We look at near-term weather forecast, any terrain data relevant to our plan, and recent avalanches. When we get to the trailhead, we continue this activity and assess weather as we find it. We look for obvious signs of recent avalanche activity. We may dig a quick pit to get a sense for stability and see how it matches what we expected to find. In the bullseye, we are continuously assessing hazards as we're traveling on the mountain. We are looking for changes in weather. We're digging pits and assessing stability. We're looking for obvious signs of recent avalanche activity. We are assessing the terrain for hazards such as terrain traps or wind-loaded slopes during our travels. We're actively looking for signs of instability throughout the trip. We'll come back to the bullseye model throughout our discussion. So let's dig into the triangle variables. Most of this should be a review from previous modules. Let's start with weather. The key question we're trying to answer is the weather making the snowpack less stable? We assess this by looking at past weather trends, current weather projections, and critical weather parameters such as rate of precipitation, any rapid rewarming, wind speed, and direction. So what are the weather trends we need to be monitoring? Any prolonged cold spell is cause for concern due to persistent weak layer formation. Any rapid, heavy precipitation can lead to rapid loading and instability. This is a big factor on Mount Hood. Any rate over 1 inch per hour is a red flag for rapid loading. High winds, greater than 20 miles an hour, can redistribute snow and rapidly increase loading on lee slopes. Temperature changes during a storm can be a cause for concern. Any upside-down storm, that is a storm that starts out with cold temperatures and then followed by warming temperatures, is a red flag. Rain on snow is also a concern. Rain adds weight without strength. Any of these should be a warning of potential instabilities. So let's use this information to begin to construct our bullseye model. This slide shows the kind of weather data we might collect. In our pre-trip planning, we would look at weather reports from NOAA or NWAC, for example. We would look at recent weather trends and projections for the time period of interest. We would look at precipitation history. How deep is the snowpack? We would look at the wind history. Where might we expect to find wind-loaded slopes? At the trailhead, we would assess the current weather. Does it match the forecast data? Any factors that can contribute to instability? During our travels, we would monitor the weather for changes. Are there any changes that are going to increase snowpack instability? So let's move on to terrain. The key question is the terrain capable of producing a slide? And if so, what are the potential consequences to us? The key factor is slope angle. Is there any slope we're traveling on or below that is greater than 30 degrees? Are there any signs of recent avalanche activity? This is a big red flag. Secondarily, what is the aspect of the slope we're traversing? Sheltered aspects can be more susceptible to surface hoar or wind loading. The link on this page shows several routes on Mount Shasta. Check it out and assess the risks and how you would mitigate these risks on each of the routes. We're going to discuss this further in class. Other terrain considerations include the nature of the slope. Are we going through a forest or across an open slope? If a forest, are the trees packed tightly together or spread out? Are we going to be exposed to any terrain traps? And the big question, are there signs of recent avalanche activity? As we've seen in past discussions, certain topology can act as stress amplifiers. Convex slopes, isolated rock outcroppings or trees, sun and shade lines are all weak points that could fracture and release. Are there any of these on the terrain we're traveling? Where are they in relation to a route of travel? Evidence of rapid loading should also be noted. Cornices, lee slopes, increasing wind-aided deposition can all rapidly load a slope and should be noted. All of the items we've discussed can contribute to instability. So let's go back to our bullseye table and look at terrain factors. In our pre-trial planning, we can look at slope angles on maps with the aid of CalTOPO's slope angle feature. We can identify hazards such as terrain traps. We should also be combining our weather info with the map and identify ridges that may be subject to wind loading. We should also be looking at potential safe routes of travel, avoiding the hazards we've mentioned here. Once at the trailhead, we should be calibrating what we see in front of us with what we expected to find based on our pre-trip planning. We should also start looking for any obvious signs of instability. Are there signs of recent avalanche activity? Can we see wind loading on lee sides of ridges? As we travel, we're going to be constantly reassessing the terrain. How do we feel about the safety on the route we had planned to take? Are there safer routes? Do we see isolated slopes that are higher angle that we need to avoid? Are we traveling below stress points that might fracture? And of course, the biggie, do we see any signs of recent avalanche activity? Let's turn our attention to snowpack. In evaluating the stability of the snowpack, we're going to look at three elements: strength, structure, and energy stored in the snowpack. We'll be evaluating strength through the use of a variety of tests, the most important of which are the compression test and the extended column test. We will evaluate structure through a series of parameters we'll call lemons. More on this later. And we'll look at energy stored in the snowpack through a quality factor that is evaluated as part of our strength testing. The key question with the snowpack is, can the snow slide? Is there a cohesive layer over a weak layer that could result in a slab release? There are clues we can look for that should motivate us to look critically at the snowpack stability. These include surface hoar, rime ice, cornices, snow pillows, grauple, ice crusts, and similar structures that indicate loading and potential weak layers. We have a variety of tests that we'll use to assess snowpack strength. The tests are all conducted in snow pits. Snow pits should be constructed in snow located on a similar slope angle and similar aspect to the slope we're concerned about, but with no consequences if there's a slide. The main tests we'll use are the compression test, which is used to assess if a weak layer will fail when triggered, and the extended column test, which evaluates fracture propagation. There are other tests we'll practice on our field day, including shovel shear test and roots block test. The compression test evaluates an isolated column of snow for the likelihood of a trigger event under increasing trigger forces. The table on the right indicates the categories of failures. Anything other than hard or no fracture indicates stability. Let me repeat that. Anything other than hard or no fracture indicates instability. The extended column test measures the likelihood that a failure in a weak layer will propagate. In this test, we again isolate a column of snow, as in the compression test. However, in the extended column test, the column is 3 times as wide as in the compression test. When the same triggering forces are applied as in the compression test, we look for weak layer failures that indicate where the force is applied under the shovel and then propagate across the column. Any fracture that propagates indicates unstable conditions. Again, let me repeat that. Any fracture that propagates indicates unstable conditions. In this slide, we summarize the test scores that would indicate unstable conditions. We'll discuss this in much more detail in our field session. I would like to emphasize that these tests are not done one time while traveling. They are done periodically in order to see if snowpack stability has changed as you've gone to different slopes or even different areas of the same slope. When in doubt, stop and dig a quick pit and see what the snowpack tells you. As mentioned previously, quality factor is an indication of energy stored in the snowpack. Higher energy leads to increased likelihood of a slide in the event of a weak layer failure. Quality is assessed by looking at the surface of the snow at the fracture plane. This is done as part of the compression test or extended column test. Very smooth surfaces indicate high energy, Q1. Ragged, irregular surfaces indicate Q3, low energy. Sometimes snowpack stability tests will indicate a strong snowpack, but the structure of the snowpack, with for example buried depth hoar, would lead us to suspect instability. In this case, the snow pit test could be giving us false negative, test results that indicate stability with a snowpack structure that would indicate otherwise. In order to determine whether it's safe to proceed, we look at 5 parameters that have been associated with false negative results. Snow scientists have determined by studying many avalanches that these parameters have a high correlation with avalanche events and are therefore useful predictors of avalanche risk. We call these parameters lemons. This slide shows the 5 parameters and associated values of concern. Let's go through them. Lemon number 1, any weak layer in the top 1 meter of the snowpack. This could be buried depth hoar, grauple, rime ice, or just sugar snow that could be a point of failure. Lemon number 2, any hardness difference across a fracture plane of greater than 1 step. We will cover the hardness scale in the field session. This lemon should be evident in the snowpack tests we'll do. Weak layer thickness, lemon number 3, weak layer thickness less than 10 centimeters. Again, we can measure this in our snow pits. Lemon number 4, persistent weak layer grains at the fracture plane. This could be any unbonded or poorly bonded snow crystal type. Lemon number 5, grain size difference across the fracture plane of greater than 1 millimeter. If we have 4 or 5 lemons present in our snow pit, we should assume unstable conditions irrespective of our snow pit results. So now we've been collecting our snowpack data and observations. We have a lot of data points. We have data and observations from the trailhead. We have data and observations from our pre-trip planning. We have data and observations we've gathered from along our route. How do we sort all this out and convert data into good decisions? The important rule as we stated many times in this presentation, is to prioritize evidence of instability above all else. Evidence of instability outweighs evidence of stability. So any recent avalanche event, woofing noises, shooting cracks, recent rapid loading, and the like should outweigh a snow pit test that indicates stability. Note that spatial variability exists. The snowpack is not uniform across a slope. Variability exists in certain specific locations on the slope, may be very unstable relative to the rest of the slope. It's these localized points of instability that will trigger a slide that brings the whole slope down. Unfortunately, when we dig pits, we're only dealing with data at that specific location. The lemons we've just discussed, or evidence of recent avalanche activity we just mentioned, are much more indicative of conditions across the slope as a whole and should be weighted much more heavily than data from any individual pit. Another useful mnemonic for prioritizing avalanche data is ALP truth, or the obvious clues method. ALP truth consists of 7 observable phenomena that correlate highly with avalanches. The observable phenomena are listed on the slide. Avalanches in the last 48 hours, loading in the last 48 hours. Are we going to be on a path of a prior slide or potential slide? Are there terrain traps we'll be traveling through? Is the avalanche rating considerable or higher? Are there any signs of unstable snow, for example, cracks or woofing, snow stability test indicating instability? Are there any evidence of instability due to thawing? As the slide indicates, 92% of avalanches occur when 3 or more of these elements are present. There's one other source of avalanche data that I'd like to discuss briefly. This is the Forest Service Danger Scale. The Forest Service publishes avalanche watches and warnings when conditions exist that could lead to avalanches. Warnings are issued when conditions are such that the avalanche danger is high or extreme at or below 5,000 feet on Mount Hood. Avalanche watches are issued when conditions are such that the Forest Service believes warnings are imminent. So the Forest Service publishes the danger scale shown on the slide to give an indication of avalanche danger. Note, this scale identifies travel advice, the likelihood of an avalanche, and the potential avalanche size. Most avalanche accidents occur in considerable conditions. So let's read what considerable means. So under considerable, the travel advice is dangerous avalanche conditions, careful snowpack evaluation, cautious route finding, and conservative decision making essential. The likelihood of avalanches, natural avalanches possible, human-triggered avalanches likely. Avalanche size and distribution. Small avalanches in many areas, or large avalanches in specific areas, or very large avalanches in isolated areas. So considerable is not safe. And most accidents happen in considerable because people interpret considerable as not dangerous. They see moderate and low and they're not worried about it. They see extreme and high and there's no way they're going on the mountain. Considerable is in that gray zone in between for most people and they just don't take it seriously enough. But as you can see from this scale, considerable conditions call for careful snowpack evaluation, cautious route finding, and conservative decision making. These are dangerous avalanche conditions. So let's go back to our bullseye model and fill out our snowpack data. At home, we studied recent AVI reports for the area of interest and tried to predict what the snowpack would look like based on the weather history. At the trailhead, we checked the most recent AVI forecast and Forest Service danger rating travel advice. On the trail, we looked at pit data, as well as for obvious signs of recent avalanche activity or instability. And of course, we're constantly updating our risk assessment as we get more data. So now we're prepared. We come across this slope, and the question is, would you ski this slope? So I'd like you to look at this and think about the parameters you would want to know in terms of the bullseye model and what we've discussed in this module, and Be prepared to discuss, would you ski this slope, yes or no? If yes, what is the route down that you might consider taking? And we'll talk more about this during class.